Hello, everyone. Welcome to my talk, Deploying Rock-Solid Applications with Kubernetes. Great to see so many people, more than I expected, but that's good. So I'm Jelmer. I work at a company called Manifold. We do a marketplace for developer services. So like we're an independent marketplace where you can get like provision, like your SaaS basically. I work a lot on Kubernetes in our stack. I do a lot of ops in that area, but I also build a lot of applications on top of that. And I do a lot of Go in that area. I've got a bunch of these stickers. If anyone is interested, you can come grab them afterwards. So this talk is about rock-solid applications, but what does that mean, actually? So the first section we'll look at is how we're going to deploy secure applications. This is not going to be at the level of a container or application. This is at the level of Kubernetes. Liz Rice already touched that a little bit this morning in the keynote. And then the second part we'll look at is highly available applications. We'll go into that in a bit. So we're all here because we like Kubernetes, I assume. We work with it. We use it. And Kubernetes gives us a lot of tools to like do a lot of things. It helps us out in a lot of areas that we had to like do manually before. Like it makes deploying applications easy. It makes scaling even easier, just changing a number. But it doesn't do these things by default. You actually have to like configure it. And especially like if you want to do a little bit more advanced stuff, you have to like dive into what you actually have to do. So in this talk, we'll look at how you can do those. The purpose of the talk is that you like have an idea when you go home to like look into these things. So disclaimer, we'll show a lot of YAML. I've simplified it. Most of it will probably not work like directly if you copy paste it, because that's like cutting it out for the slides, so you can actually read it. But it should give you a general idea of what you should look at. A lot of the resources, or like all the resources I've used, or like all the topics I've covered here, are linked at the end of the slides as well. So if we look at the Kubernetes landscape for an application, this is roughly it. In the center we have a pod, which is basically the lowest abstraction level in Kubernetes. We start there, and then we have a bunch of extra things that are linked to pods. And in this talk, we'll go over a few. We'll go over deployments, we'll go over RBAC, network policies, pod security policies, and pod disruption budgets. So the first section that I said we're going to look at is security. Again, this is at the Kubernetes level, not at the application level or container level. And Kubernetes has like 3 topics for this. The first one, RBAC, then we also have network policies and also have pod security policies. We'll dive in with pod security policies first. So by default, this is not enabled. Like you actually have to enable that with an admission controller. But then we can actually dive in and actually like install these. So this is a privileged policy. So this is like gives you access to everything. As you can see, you can like escalate to privileged, like to root. You allow all the Linux capabilities. You have access to all types of volumes like config maps, secrets, persistent volume claims. You can access the host network, and you can even run as root. What we want to do is make that a little bit more restricted, and that's what we get in here. So now we say you can't go privileged. You actually like can't go root. You can only use secrets, so you can't use config maps, you can't use persistent volume claims, so we can only use secrets. You can't touch the host network, and you're not allowed to run as root. So we define that now, but how are we going to actually like apply that to our application? And that's with RBAC. So RBAC is the next phase in that. So RBAC stands for role-based access control, and actually exists out of 3 things. So you have your service accounts, which stands for your identity roughly. Then you also have a role or cluster role, and then you also have cluster role bindings or role bindings. So the role is then defining what your access pattern actually is. So we'll start by creating a service account. In this case, it's a simple service account for KubeCon. Then we apply that. And then we can create a cluster role. Note that this is a cluster role here. As you might have remembered from the previous slides, you can actually have a role as well. So cluster roles are like scoped across your entire cluster, but just regular roles are scoped across just the namespace. So if you would have a role that is linked to your namespace websites, it's only valid in that namespace. So in your default namespace, you wouldn't have access to that. That's important to think about because pod security policies are cluster scoped by default. So you don't have to define them per namespace. So what we're going to do with this cluster role here is we're going to define that we're going to use these pod security policies, and we're going to reference the one that we created earlier, so the restricted one. We can now also link that to our service accounts that we created earlier by referencing that cluster role. So we say KubeCon security, and then we're going to link that to a subject. In this case, or subject is a service account. You also have some different ones, but we're not going to go into that. So we link that to the KubeCon service account now. So we have this all set up now. We have our cluster or roles linked to our service account, but now we actually have to link that to our application as well. And that happens in the deployment, or in the pod more precisely. So we can actually define a service account name. So we're going to reference KubeCon here as well. And now that means that that service account is linked to that deployment. So every time you do deploy that service account is taking is the identity for that deployment. So we have roughly secure applications now. We secured that. But as Liz Rice showed in her keynote this morning, we also have this API server which pods can speak to. So how can we secure that now? A simple way is to disable auto-mounting that service account token. If you remember from the keynote again, you can load that token file, and then you actually have access to the cluster API, which you don't really want to do. So you can disable that by default. But some applications might actually need to have access to the cluster. So for example, if you use Cert Manager, for example, or if you use Contour, they actually need to speak to the API to get some information out. So you want to give some specific rules that they can actually do. And how you can do that is with RBAC again. So you can make another cluster rule and say, oh, in this case, we're going to make a rule that says this account can actually use the secrets. So we can actually get the secrets out. So this one can only get the secrets out, so it can't read, or it can't delete, or it can't create. It's just getting them. And you can do that with any resource that you want. So we now have secure pods, also security interaction with those pods between the pods and the API server. But what about the interaction between pods themselves? That's where network policies come in. So this is a rough diagram that you can make. You can say, oh, we have an ingress, maybe Envoy, and then we have a few applications. Some are open, some are very restricted. So you can actually control that incoming and outgoing traffic. So this is an allow all configuration, which basically means obviously allow all. So you can allow all incoming and outgoing traffic. And this is a default. So if you enable network policies, this is default, not nothing else. But then we can restrict that a little bit more. So in this case, we have a quart deployment, and then we say for the network policy, the pod selector is an important part on this. So we're going to find the pods that have the label linked, the app label linked, which are this application that we want to deploy. And then we're going to say the ingress, the incoming traffic, we're going to restrict that to the ingress controller namespace. And we're going to restrict that to the pod that has the app Nginx linked to it as well. So only pods that are Nginx from the ingress controller namespace are allowed to speak to these applications. There's one caveat to that, and that it depends on the network plugin that you have. So some implement all of this, you can control incoming and outgoing traffic. Some only do incoming traffic. Some don't do none of it at all. So depending on that, you'll have a little bit of differentiation. So we have a secure setup now. We covered that part. It's time to go into the high availability section of this. Before we dive in, I want to clarify as well what we mean with high availability. this talk is not about high availability for like your nodes. We're purely going to talk about high availability for your applications. And there's other talks about like how you can actually set up a high available cluster and stuff. And we're not going to dive into that here. We assume you already have that. So the first thing that like, not the first thing we want to look at, but high availability is like if you have an application, if one of your applications fails, you want to make sure that your users still get to see something, right? So you're going to deploy multiple of these applications, and then if one fails, the other ones take over, and you still have that interaction. That also works for internal traffic. So you might have a circuit breaker somewhere, and then if you go from application 1 to application 2, you have some communication, you want to make sure that that responds properly. Because we work in a distributed environment, we want to make sure that we, if something happens, like a network fault, we can still get the response back. So for this high availability part, we're going to look at two sections: deployments, which also have replica sets, and then also pod disruption budgets. So with deployments, they're basically a functionality on top of replica sets, and the main thing that they add is replicas and update strategy. So with replicas, it's easy to scale, so you just change that number, and then it will scale to that. And then the update strategy is actually quite interesting, and that's how we can define how we roll out our application. So we can say, this is the way, if we scale, that it should happen, or if we deploy a new version, this is how it should be rolled out. This is a simple template, and we're going to start with that. So we just say, we're going to deploy 2 replicas. We're not going to think about update strategy yet. We're going to just use the default that Kubernetes provides, and we're just going to deploy 2 applications. So what happens here is we deploy that. We have 2 version 1.1.0, and that's running nicely. We have a service linked to that that does load balancing, and then traffic flows through both of these. But what happens if we do a deploy? So the 1.2.0 version gets deployed, and immediately the 1.1.0 version gets terminated. But the more important part here is that we lose high availability, basically. Because, well, as you can see, the 1.1.0 is terminated, but 1.2.0 isn't booted yet. It takes a while to do, and in that like brief moment, we actually serve only 1 pod. So we have to think about that. Eventually, this 1.2.0 pod comes available, and then we have high availability again, and then the cycle repeats until all 1.1.0s are done, and everything is the new version that we want. But what if that new pod doesn't come available? Then you're in a bad situation where you only have 1 pod. And because your deployment is on the new version, you can't really like trigger a new 1.1.0. You could do a rollback, obviously, but. So a way to fix that, or no way to fix that, this is a default configuration, actually. So by default, we're going to have a rolling update strategy with a max search of 25% and a max unavailable of 25% as well. The important thing to remember here is that these numbers, they get rounded up. So that means in case of 2 replicas, you actually get 1 max unavailable. So that means that if you do deployments, whilst you're deploying, Kubernetes tolerates 1 unavailable pod in your cluster. The max search is saying that the amount of pods that it's going to create extra. So if you have 2, it's going to create 1 extra pod. You could set that to 100, and then it's going to deploy 2 extra pods. You have to like play with those values a little bit. But for this example, we're just going to have a look at what happens if we set this to max unavailable to 0, which is a little bit more interesting and maybe a little bit more desired. Actually, just a quick note on that, like if you have more replicas, you still want to think about these numbers because the behavior is similar, and you have to like fine-tune that yourself. So again, we start with the 2 1.1.0 versions, and then we do deploy. So what we see here now is that this new version becomes available, but we maintain this high availability, which is good. And then eventually, the new version becomes available. We go to all the pods, and then Kubernetes actually like terminates that last one, or the old one. And then it repeats that cycle and it goes through everything again. But the interesting part here is if that new deployment fails, like you don't have an issue. You get alerted because one of your pods is not like spinning up, but you can like still like serve traffic and you don't have performance degradation. And again, if you have more replicas, you might not go to like one pod, but if you have 100 replicas, the question is, can you tolerate like, for example, 25% of that going down while you do a deploy, which is probably not the case. So you want to definitely fine-tune those numbers. The next section we want to look at is affinity. So with affinity, you can say, I'm going to deploy these applications on a specific set of nodes or regions. There's a few areas that you can, like topologies that you can look into, basically. We're going to look at host here. Before we dive into the code, let's just have a quick look at what happens if you don't define anything. So we have two zones here with each with 2 nodes, and all of a sudden node 3 goes out, which is fine. We're running Kubernetes, it's going to take care of this, right? But note that in node 1 we only have 1 application running at the moment. So what Kubernetes is going to do is going to see, oh, this node 1 actually has a lot of resources available. So it's going to reschedule those faulty applications on that node 1, and it's going to be happy. The issue with that is, there's actually 2 issues. So the issue with that is that node 1 now has 2 app 1s. So if that node goes out for some reason as well, we lose like a lot of capacity. But if you look closely, application 1 is only deployed in zone 1 now. That means that if zone 1 goes out for some reason, it happens, like we lose application 1. So what we want to do is we want to define some affinity rules. So again, this is a deployment, and then we're going to define affinity, and we're going to use anti-affinity here. So we're going to say these rules, like we don't want to adhere to that. Like we don't want to do the reverse, basically. And we're using preferred during scheduling. You also have required during scheduling. The preferred during scheduling is basically saying to the Kubernetes API, like we prefer that you like do not deploy this on this machine if these rules already apply there. But if it is the case and there's nothing else, you can still do it. If you do require it, it's not going to deploy it. We chose to do the preferred and then set up alerting on that to like make sure that we still have enough capacity, and then we can like look after it once we have the alert. But at least we still have the same amount of like replicas running, so we can make sure we can serve traffic. So what we're going to do here is we're going to do that pod affinity term, and we're going to do label selection again. Again, we're going to select that same application, and we're going to say, oh, is this application already running on this host? So what we're going to do here is we're going to determine, like, does this host name, like the machines with this host name, does this already have this application running? And then Kubernetes is going to determine, like, oh, it does, so I shouldn't schedule it on that. So if we look at that now, what's going to happen instead of putting everything on node 1, it's actually going to say, oh, node 1 already has this application 1, so I shouldn't schedule it there. And definitely like node 4 doesn't have this yet, so oh, I'll prefer to schedule it there. And that's a nice way to like make sure you like spread load across your nodes basically and your regions. So the example here was cut out, so we actually have some rules set up to do that across regions and zones as well. So we talked about like disruptions or like unavailability due to like external events like node outage or zone outage. But what if your application is having an issue? Like, how does Kubernetes know that? Like, when we talked about deployments, we said, like, this application needs to, like, we want X amount of applications to be available, but how does Kubernetes know that? And that's where probes come into play. So there's 2 types of probes. There's your readiness probe, which basically works for determining if your application is ready to serve traffic. So if you have a boot, like a longer boot time, you probably want to play with these initial delay seconds or period seconds. And that's basically like until, these checks basically run until like your application is ready to serve traffic. And then you also have the liveness probe. So once your application is running, you want to make sure that like it's still healthy and you can still serve traffic to that. And that's where the liveness probes come into play. And usually those liveness probes have a shorter period second and a shorter initial delay seconds. because you want to like regularly check that. Like once your application is running, once it's serving traffic, you want to make sure that it's still healthy. And then Kubernetes is going to do reboots or whatever it needs to do to make sure it's running correctly. There's one caveat with that, and that's circular dependencies. So a lot of people set up these health checks and then say, oh, we're going to check, I have these dependencies, and I'm going to check that that dependency is alive. And then if that's not alive, I'm going to fail my health check. But you might end up in a situation where you have this, where you have 3 applications, in this case A, B, and C, that all depend on each other. So in this case, A relies on C, C relies on B, and B relies on A. The issue here is that if C fails, that's not that big of a deal yet, but if C fails, the next step that's going to happen is that A is going to fail as well, which means that B is going to fail as well. And to actually get out of that, you need to like either time it very well or not use a circular dependency, basically. So we installed degraded, we added a degraded label to that. So instead of actually failing the health check, we just say that it's degraded, and that way like external monitoring services can actually detect that and just alert us as well on that. So we talked about a lot of disruptions so far. So we talked about like the expected disruptions from deployment. So if we like take out some applications, but also about unexpected failures or disruptions, like an application failure or a node failure or a zone failure. So Kubernetes does a lot of scheduling and rescheduling, and you need to make sure that Kubernetes like is aware of this and make sure that Kubernetes like knows that you definitely want this application to always be running at this capacity. And that's where pod disruption budgets come into play. So another example here is we have 4 nodes, and node 4 is just a node that just spun up, so we're scaling, or we just tolerated, or we just had node failure. So node 4 is a new node that came into our cluster. And we also have application 1 that is using a lot of resources. So application 1 is on node 1 and node 3. And then node 2 just doesn't have that much stuff going on at the moment. So what Kubernetes is going to do is going to say, oh, I can take these like high offensing applications, the applications that are using a lot of resources, and I can just reschedule them onto a node that isn't using a lot of resources. But if you notice that here, the issue now is that, well, again, our application is not available because it's being rescheduled. So that's where pod disruption budgets come into play. So again, we want to define this, and it's important to like define this correctly, like to what you need, because these objects are immutable. So once you apply it, you have to stick. Well, you can delete it and then apply it again, obviously, or replace it. But you can't just update them at will. So it's like better to use a percentage here. So that way, if you scale up, it applies to that percentage instead of like having a fixed number that wouldn't really scale. And again, the percentages are being rounded up as with the update strategy. So what's going to happen now? Again, we start with this beginning phase. And Kubernetes is just going to say, oh, I'm going to redeploy this app 1 that's using a lot of resources. I'm going to redeploy that on this node that doesn't have anything at all. And then I'm going to, in the next phase, when application 1 has become available, I'm going to take application 1 from node 3, and I'm going to put that on node 2. And that's basically rescheduling. So we kind of want to prevent all of this misconfiguration. And how can we ensure all of this is set up correctly? So there's a lot to think about here. We have to think about pod disruption budgets. We have to think that we set up these update strategies correctly, that we have replicas set up. Yeah, we have to think about a lot of things. And that's not always the nicest thing to do. Can we avoid that with linting? Linting is like a lot of work. You have to like set that up correctly, make sure it's like up to date. It's quite fragile as well. You might miss something if your linter isn't isn't configured correctly. But the biggest issue is that if you just don't run the linter, well, then you can still deploy all of this to your cluster, right? So what we want to do is want to use webhooks. So Kubernetes has webhooks, and as we saw in the keynote this morning, we can do validation. We can also do changes upon admission. And that means we can't bypass that linting. So it's actually in the cluster. So if you deploy that into your cluster, it will definitely get validated properly. And again, Liz touched on this in her keynotes. She used the open policy agent. And in this example here, we're going to just use another tool called Barbosa. So quick overview of the webhooks again. So if you do a request or if you do kubectl apply, you're going to go to the API HTTP handler. That's going to do like some authentication and authorization. And then you're going to hit the mutating admission controller. And it's going to see for this object, so in our case, a deployment, is there a webhook that is watching this? If it is, it's going to go to that webhook, and then it's going to do its mutation that is needed. So you could even have a mutating webhook that says, I'm going to make sure that all my applications at least have 2 replicas running. Or you can do like automatically spin bot disruption budgets and stuff like that. Then you also, we also do like a very light schema validation. So every object has JSON validation. Even if you use custom resources, you can define that. That's quite lightweight. And then we also have the validating admission controller. So the validating admission controller is going to do what Liz showed this morning. And it's going to like take that object. So again, our deployment is going to take that object and it's going to validate that against a set of rules that we have defined. And that way, by having this, we enforce at the cluster level that you have all of these policies set up. And if you don't pass this validation, it's obviously going to error on your side. If you do, it's going to be persisted to etcd. So again, in our case, we're going to have this simple example here. We're going to apply that 1 replica. That's the important part, and no update strategy. So we're going to apply that, and we see, oh, this deployment is successfully created. But now we're going to say we're going to have a high availability policy. So again, this is like specific to the Barbosa tool. You can do this with OPA as well. It's just the syntax is a little bit different. This is like with custom resource definitions. So what we're going to do here is we're going to deploy this high availability policy in a namespace. And then we're going to say this applies to all pods. So we use the selector here, which is again a label selector. And the reason for that is that you can actually start mixing. So you can have a policy that says all pods should have a label, for example, team. And then you can start making availability policies based on teams. So then you can have a selector based on a team label, which is quite neat. And then we're going to say you need at least 2 replicas. So yeah, we want that to like at least have some high availability. And then we want to make sure that our strategy is rolling update, not recreate, because we don't like recreate. And then the minimum surge that you're going to do is 25%, which is fine, and maximum surge is 50%. That's to make sure if you have like a bunch of replicas, because we have a minimum, but we haven't specified maximum. So you could have like 100, and if you would say max surge is 100%, then all of a sudden you spin up 100 extra pods, which you can do, but you need a cluster autoscaler. So we want to limit that as well. And then we want to say the max unavailable, in our case, is going to be 0. You can make this percentage based as well. So we're going to apply this policy. Great. And then what happens if we apply this deployment, we see that we have 2 errors. The first one is that the replicas is invalid. We want at least 2, but we have 1, so that's not valid. And then we also see that the max unavailable is invalid as well. So we have 25%, and again, this is rounded up. So if you have 2 replicas or even 1, the 25% is going to be rounded up to 1. So it's more than the at most 0, so it's going to fail on that as well. Yeah, so webhooks. So this is using Barbosa. The main difference is that Barbosa would do admission webhooks as well. but the OPA stuff works great as well. So that's it. If you're interested in all this stuff, Manifold is hiring, so definitely come reach out. Yeah, that's it. I'll be around for questions if you